All right, welcome to today's lecture where we're going to be again focusing on motion in one dimension, but we're going to start moving to the fact where we're going to have equations in the third video. In this first video, in the second video as well, we're going to kind of just discuss some classic, or I don't want to say classic, some general things to consider moving forward in the class. It's physics based, but it is kind of a little bit of, hey, we are building up ready to solve problems in this class using mathematics and some standardized steps. So last time we introduced a couple of different terms. So we had motion diagrams that were used to visualize the simplified motion of an object. So we had points as specific time apart. The points were the position. We could look at the change in position, which is defined as the displacement. It is a vector because we are moving in a direction. We then, because those points are an equal amount of time apart, we can divide by time and we get the velocity. So how fast and in what direction is our object moving? And then we have the acceleration as well, which is a change in velocity over time. So with our equations for average velocity and average acceleration, here we have the word average, but we are going to be dropping that moving forward. And the only time we will be specifying a different type of acceleration and a different type of velocity, but we're not going to deal with that until our next lecture next week. So today we're going to talk about motion in one dimension. So like I said, we're going to focus on signs for that. In the next video, we're going to talk about problem solving in physics, just general steps in which we're going to be using. And then in the third video, we're going to talk about motion with constant acceleration, but we're only going to look at the second half of the section. The entirety of the first part of the section, as well as the other early parts of chapter 2, we'll be discussing next time. I wanted to introduce the equations first that we're going to be looking at because I want to give you guys a little bit more time in your calculus classes to hopefully see the derivative there first. I know that's probably not going to be the case for quite a few of you, but I just wanted to see if there's just a little bit, one extra lecture gets you there or not. So let's talk about motion in one dimension. So in general, motion is described with a position. The position we are going to be using has a vector r. So this is the standard position vector. That way when we have the displacement, it's delta r. We have the velocity and the acceleration. So again, each one of these is a vector. So we need the magnitude, the value of it, and the direction of it as well. So we're going to focus on one-dimensional motion. So in this class, we are very rarely going to be using all three dimensions. So we're going to ignore z 95% of the time, if not 99% of the time in this class. Once you get into Physics 230, that's where three-dimensional problems start becoming a lot more relevant. That's going to be where you need a third dimension. So we're going to focus on either having motion in the x direction or the y direction. Today we're going to be focusing on the x direction. In our next lecture, we'll talk about the y direction. But that means that when we write out our variables, our position, we could have it as x or y, depending on the direction we're moving in. Velocity, we have v. We indicate the direction with a subscript, so we have v sub x or v sub y. And we do the same with the acceleration, where we have a sub x or a sub y. That subscript indicating which direction our object is moving in with that velocity or that acceleration. So position, velocity, and acceleration are all measured with respect to a coordinate system. Now this coordinate system could be given by the question, or you can give it to that particular question. So typically we are going to want to choose a coordinate system that makes our life as simple as possible, whatever that ends up actually being. So the goal is to make it as simple as possible, but we need to always make sure we are identifying the coordinate system we are using. So in order to have a coordinate system, we need two things. We need an origin and we need some label axis. So a very kind of common thing that the textbook is going to do is you'll have an object at some location and they'll put the origin in the middle of the object and they will write something like this. This indicates that x is equal to 0 and y is equal to 0 in the middle of the given object. This is one way you can write out your coordinate system. Another thing that this is the way that I usually do it, is I draw my x and y coordinate system, and then maybe I draw, so it indicates where my origin is, and then maybe I draw my whatever on top of it. The third way in which we can indicate a coordinate system is we have our object. Some people like to not have anything near their, let me draw that somewhere else. So you have the object, they just draw the coordinate system kind of floating away from it, and then they put the point where they want it to be. So any of these different methods can work out. It's going to be your choice, but you are responsible for indicating what your coordinate system is. So if we were using our traditional coordinate system, which is what I've drawn here, right and up are the positive x and y directions respectively. And that means that left and down would correspond to the negative x and negative y directions respectively. So when we would go in and write, if we said our value was -2, 0, that would indicate that our object is to the left of our origin 2 spaces. So that tells us the direction in which our object is located. It is to the left of our origin. This is why it's going to be important for creating a coordinate system, because if you don't do that, and let's say you said to the left was positive, I'm going to be assuming you used a standard coordinate system and all your stuff is going to be off by a sign. So it's important to make sure that you show your coordinate system, because what that does is make sure that when I look at your question, I know what signs you should be using. So, this is the standard coordinate system. You are an adult. You can choose a different coordinate system if you want to. If you always want your object moving in Z because you really like writing out Z's, that's perfectly fine. Just, draw a coordinate system and say, I'm moving in Z. So you can choose the coordinate system you want to use. I will always try to use, I'm going to try to be matching the textbook as we go through this semester. I won't always be. I have some, I personally am not a huge fan of this method here. I think it gets pretty messy pretty fast. So I don't use this, but I am going to, try to make sure that if the textbook says that X is to the right, I'm going to try to do that as well. So this this is a tactics box from the chapter, and it tells us, here we have our positions, the left side here being X-based and the right side being Y-based, and it tells us how our values would be greater than or less than 0, depending on the direction they point in. And there's also a summary as to what is happening with our position, velocity, and acceleration. Again, this is focused on a one-dimensional situation. So Here it says the sign of acceleration tells us which way the acceleration vector points, not whether the object is speeding up or slowing down. So here we have, the object is accelerating to the left. The object is accelerating upwards, and all of this uses the standard coordinate system in order to identify a positive or negative value. So let's talk about acceleration and sign in a little bit more detail. So position, personally, feels like it's the easiest of them because that's how you have used coordinate systems in math previously. If it's to the right, it's positive. If it's up, it's positive. If it's to the left or down, it's negative. Velocity kind of follows the same general trend. If I'm moving in a direction, it makes sense that I am positive or negative. Acceleration is different. And that's because how we personally think of acceleration in our day-to-day lives and how acceleration is in physics don't 100% match up with how signs are used. So naturally, when we think about acceleration, that indicates to us that we are speeding up. And when we're stepping on our brakes, or we stop running and we start slowing down to a walking pace, we would refer to that as deaccelerating. And based on that, because accelerating has us, with how we think about it, as we're speeding up, we would think of it as positive. And because we are slowing down as we deaccelerate, that would indicate that it's negative. That is not how this works in physics. In physics, deaccelerating does not have to be negative, and accelerating does not have to be positive. The direction of the acceleration vector is what is going to be used to determine the sign. So if we're speeding up in the negative direction, our acceleration value is negative, because the acceleration vector would be pointing to the left. So for one-dimensional motion, this is kind of how we can remember acceleration and sign. If an object is speeding up, so that it is getting faster in a given direction, positive or negative, that means that the velocity and the acceleration point in the same direction and have the same sign. The acceleration is working in such a way that the velocity can increase. Again, this can happen in the positive direction or the negative direction. So if we were to kind of draw this out, we would have, let's say we have some points. Our objects, we're going to be, let's say we're moving to the left, or sorry, we're increasing. So we're going to be moving to the right. And our acceleration is also pointing to the right. So this is how, on a motion diagram, an object speeding up would look. Now we could obviously have the other case, where an object is slowing down. And in this situation, the velocity and acceleration have to have opposite signs. So let's have the case where our object is going to be moving to the left. So here we're moving left. And our acceleration is pointing to the right. So even though we are slowing down, our acceleration in this particular instance is positive. So here, we need to be aware of, if we are speeding up, again, this is for one-dimensional motion, if we're speeding up, the acceleration and velocity point in the same direction. If we are slowing down, they point in opposite directions and they would need to have opposite signs. So with accelerating or deaccelerating, it does not matter that doesn't instantly indicate the sign of your acceleration. Now we could also have the case where our object's velocity is constant, and in that situation, the acceleration would have to be equal to 0. And this same set of definitions works in the y direction as well, where if your object is speeding up, if the velocity and acceleration in the y directions point or have the same sign. So if they point in the same way. So the same analysis works for the y direction, just right now we're focusing on x. So we're going to spend more time, not in this lecture, but in the next lecture, looking at some graphs. I just want to quickly go over some position versus time graph stuff because it is kind of heavily emphasized, like I said, in the next lecture. So I just want to talk about it briefly here. So for any type of graph, you put that independent variable on the x-axis and the dependent variable on the y-axis. So here, if we have position versus time, we need to think about how we define a position. The position, as we talked about, is where an object is located at a given time. So that means that our time is our independent variable. It is going to be going on the x-axis, and the position is dependent, and it is going to go on the x-axis. So basically, the position versus time graph is another way in which we can have a motion diagram, except for now we're explicitly looking at how the object moves, not in space, but how the object moves in time. Now, we're not going to be doing it today, but we can use the position versus time graph to help us find the relationship between position, velocity, and acceleration. So this is going to be what we focus on in the next lecture, so next week, Wednesday, because Monday is going to be a holiday. So we will get to this relationship here, just not today. So this is just an example of kind of what's going on. So this is our motion diagram without the acceleration. So here we have our points. They are given in the x direction. So with a motion diagram, visually, we can see a little bit of information, but it can be hard. If I look at one of these points, let's say this one here, unless I get a ruler and I measure out values, I'm not going to know exactly what this is. I can guess. I'd say it's maybe 330-ish meters, but I don't know the exact value. And I'm going to have that same problem kind of coming up a lot. So maybe this isn't the best way to represent my data. Now, here I have a table that tells me where these data points are located. So here's time is 0 at 0. A minute later, I'm at 60 meters, and then 120 meters, and then 180 meters, 200 meters, and these are the times that correspond to the position. Now this is, personally for me, a lot more useful than trying to draw this out. However, it only tells me the position and time. So, like I said, what we're going to be getting into is looking at how to use position versus time graphs to get information about the velocity and the acceleration. So, as a table, this doesn't really help me out, but I can put that in a position versus time graph. I've put my independent variable time on my x-axis and my dependent variable x on the y-axis. And here, all of these points are explicitly labeled for where my person, it says student walking to school, so where the student is at a given time. So these are the explicitly given points. However, I can connect these. And I'm trying to connect it with a smooth line, but I'm bad at that. And it's supposed to go through all the middle parts because I know my person doesn't teleport every minute. If we could teleport, I'm not going to teleport 9 times to get to school. I'm going to teleport once. So if I'm walking, I have to go through, in this case, 0 meters to 540 meters. So I have to pass through all of these different points in order to actually make it to my distance. And it's this line that we're going to be using next lecture in order to go through and try to start solving for things like velocity and acceleration without having to try to use graphical representation and some guesswork as to where points are. All right, so that's going to wrap it up for this first video. Make sure to watch the next 2 videos as well.